All right. So we're going to start the final session before the exercises, which just consists of one talk. We're going to shift everything, since we're running behind schedule a little bit, by a half hour. So the exercises are going to start at 4:45 instead of 4:15. Tamara Broderick is going to give the last talk of the day, which will close the final gap in your understanding at the higher level of the machine learning component in AMP and of clustering, which is going to be what you'll do in the exercises. Tamara is also a machine learning student of Michael Jordan's and is a fourth-year student and very excited about the remaining stint she has here working with Michael Jordan on machine learning.
Is this on?
No. Push and hold.
Oh, push and
Until it turns green. Great.
All good?
I think so.
Okay. Okay, great. Thanks to those of you who continue to show up, even though this is the last session of the day. Thanks, Andy, for that introduction. I'm going to be continuing with the part 2 of our machine learning crash course, in which, of course, you will be learning about clustering. But as we've already said a few times today, we're really focusing on implementability. We want you to come out of this machine learning crash course able to code up this algorithm, or able to code up a clustering algorithm yourself. And so the algorithm I'll be teaching you is k-means. And I also want to give you a little sense of nuance to do with this algorithm, that machine learning in general, and k-means in particular, aren't just black boxes. That you don't just put your data in and get some magical perfect results out. And then hopefully, time permitting, I'll go through an example of what you need to do before using k-means, and the sort of analysis that you might do afterwards. So let's start with clustering. The fundamental idea of clustering is that you have a set of data and you want to find some underlying structure in that data. And when we're using clustering in particular, the structure has a particular form. So clustering is grouping data according to similarity. This is a pretty vague definition. Let's go through each of the key points here: data, similarity, and grouping. For data, we might have this sort of cartoon example. We have an archaeological dig, maybe. And each of our data points is some sort of archaeological artifact. And our features are the distances east and north, maybe, of some base station. So what's a similarity that we might have? Well, a very natural similarity in this case is to say that two artifacts that are close are similar, and two artifacts that are far away are dissimilar. And now finally, we want to group the data. And I think it's very natural to see what these groupings are going to be. We want to group the close objects into groups that we call clusters. Another way that I might represent this is just outlining the clusters, but most of the talk I'll be using this color coding scheme. How is this different from classification, which we just learned about? Well, the key idea in clustering is that you have a bunch of data, and all of the structure is latent. You don't know what the groups are in advance. In classification, we knew the meaning of the groups in advance. So for instance, consider our archaeological dig example. We might find these groups in our data, and then we would say after the fact, oh, okay, so I see these three main groups. What's their meaning? Maybe they correspond to families and the sort of urns that they've spewed out back in the day around their homes. But if we were doing classification, we would know that in advance. We would know, hey, this is actually family A, this is family B, this is family C. And instead of finding structure in all of the data, we want to predict the values on some new data. So using the old known labels, we want to predict on the new labels. So we actually have some sort of fundamental information beforehand. We don't have that in clustering. So why would we do clustering instead of classification? Well, the first example is exploratory data analysis. And this is generally a good idea. You have a new set of data. Before you dive into that data and try to get some results from something like classification or regression, you want to familiarize yourself with the data, get a sense of what sort of information is in it. So an example of this might be, maybe I have a social network. And again, we want to go through this data similarity grouping paradigm. So what's the data here? Well, the data is fundamentally a person, but I think we learned from Ariel's talk that that's not enough. We need a featureized vector to put into our algorithm. So let's be more concrete. Something that we might put in to represent a person is some sort of vector specifying that person's interests. So there might be an element of the vector for each interest, and then we have a 1 in that element if the person has that interest, and a 0 if they don't. And then it's easy to calculate a similarity, which is the number of common interests of those two people. Some other reasons that you might use clustering instead of classification are as follows. A lot of times, the classes or the clusters are just unspecified. You don't know them in advance. You have to use clustering. You have no choice. So an example of this is something like topic analysis. Maybe I have a bunch of documents that I give to you, and I want you to decide, with only that information in those documents, what words go together. So the kind of clusters that I might get out are things like this. See these words, new, film, show, music, movie, these are sort of artsy words. We think that they go together. Words like million, tax, program, budget, billion, federal, these are sort of money or budgetary words. And again, the key difference with classification is that in classification, we would know these labels in advance for these words, and then we would have new words that we were trying to classify. In clustering, all you have is the documents, and then you want to find these sorts of groupings automatically. So again, what's our data and our similarity? Our data is a word, but again, we want to be very careful about what we're actually feeding into an algorithm. So let's be more specific. And data in this case might be some vector indicating document occurrence. So we have a list of every document, and then we have a 1 if the word occurs in that document, and a 0 if it doesn't. And then we can calculate similarity as the number of times two words co-occur. Another example is that our classes are changing too quickly for us to label them. We're perfectly capable of labeling them, but it takes too long. So an example of this is clustered search. You know, back in 2009, if I searched for the word tiger, I might have meant Tiger Woods. I might have meant the Mac operating system. I might have meant the animal. I don't know, and so maybe I want clusters of documents to be returned depending on those different meanings. And so here, the data is a document. But again, to be more specific, it could be a vector for each topic. I say whether or how many times that document occurs. And then to get a distance or a similarity, I say how many topics are shared between two documents. And again, the reason that we're really interested in clustering here is this is already out of date. You know, now I'd be searching for lion, and maybe I mean the Mac operating system, or maybe I mean the animal. And so I don't want to keep having somebody update this. I want it to be done automatically. And that sort of comes to this next point that sometimes it's just expensive to label data. So another type of clustering that you might do is image segmentation. I want to cluster the pixels in this image. Well, some people have an army of undergraduate students who go around and they say, oh, this is a tiger, and you know, here's the grass, and here's the sand. But no matter how big your army of undergraduate students is, they will not be able to handle the billions of images that are available to you from many databases. And so you instead want this to be done automatically. So here your data is a pixel, but again, more specifically, you want to have both its color values, its RGB values, and its pixel location. And it's very important that you have both of these in this particular example because you can imagine, well, there are some colors that are shared between different clusters, but they're still fundamentally different clusters because they represent different things. And there are some locations that are quite close. You know, the grass is very close to the tiger, but they have very different colors and therefore should be in different clusters. So I hope with these past few examples that I've motivated you beyond that original cartoon, which looked really easy. I think we could all cluster that, you know, very, very quickly, and it's not a problem. But a lot of times we have data that isn't so easy to cluster. So for instance, we have high dimensional data. Maybe our data is full of words, it's full of pictures, it just exists in very many dimensions. And then I can't make this nice, happy little two-dimensional plot like I did with the cartoon, and it's easy for you to just pick out what clusters there are. And a lot of this comes back to visualization. With big data, again, you know, if I plotted all of that at once, I'm just going to have a big blob. There's no way that I can draw lines between, you know, what are the real parts of the structure. And data that's not numerical, I can't do that either. And part of this, again, too, is, you know, sometimes we need this clustering to be done in a very fast, automatic fashion, and it's not feasible for a human to be doing this. Okay, so now we know what clustering is, at least in a very vague general sense. And I think we're going to get a much more specific sense by looking at a very particular algorithm. And the algorithm I'll be showing you is k-means, which has already been mentioned a lot of times today, so I hope you're motivated to look at it. But a number of benefits of k-means are as follows. It's fast. It's scalable. It's very, very fast. The thing is, if you're going to do clustering on big data, you're almost going to have to use k-means. It's sort of the only thing that's available for very, very large data sets of the kind that, you know, we're interested in at today's mini course. But there are other reasons to use k-means. It's conceptually straightforward. I'm hoping by the end of this talk that everybody in this room is going to be able to program up k-means. In fact, that's in your exercises, so you really need to be able to program up k-means. But beyond that, it's also very popular. So if you know one clustering algorithm, it probably should be k-means. If you're going to talk to somebody outside this room about clustering later today or next week, the one clustering algorithm they're going to know is k-means. So if you want to have a conversation with them about clustering, you really need to know what's going on under the hood here, and what are the issues involved with k-means, and that sort of issue. Okay, so let's get into k-means itself. But before we do k-means, we need to build up just a little bit. So first of all, what is our data here? Well, the data that we're assuming is a vector of continuous values. And I'll get to that more in a second. But we're thinking of numbers that exist in a variety of different values. So our example with the archaeological dig is very straightforward and very appropriate to this discussion. So for instance, we might have an artifact location at 1.5 yards maybe east and 6.2 yards north. And so we would write it as this vector of values. Now our data set is going to be a collection of such vectors. So here's perhaps the third observation, like up here. But we're going to have a number of other observations corresponding to each of the other artifacts. Perhaps there are n total artifacts in our data set. And again, these are really just features. So there's a broader way of understanding this. I'm going to use the notation in general with this x with two subscripts notation, where the first subscript represents the data point. So perhaps the order I saw those archaeological artifacts in. And the second subscript represents the feature. Now, for the purposes of this illustration, I think it's really nice to be working in 2 dimensions. It's very easy for you all to see. But we don't have to have only 2 features. We could have d continuous features. OK, so that's our data. We know that the next thing we need to look at is similarity. What's the similarity here? Well, the similarity that k-means uses is the distance sort of as the crow flies, which many of you are familiar with. It's just the usual distance and is known as Euclidean distance. In fact, we'll be using squared Euclidean distance because for various reasons that's a lot easier to work with. So what does this look like? Well, the distance between this third data point and the 17th data point is just the difference in the first feature squared plus the difference in the second feature squared. And this generalizes in a very obvious way. For each feature, we just add up the differences in the features squared, the feature values. OK, that's similarity. What about the grouping? How do we describe the grouping? Well, there are 2 points I want to make here. Why is k-means called k-means? The first is you need to specify the number of clusters. Now, this is a very particular definition of clustering, and we're going to talk about other potential definitions of clustering later. But let's just roll with this one for now, OK? Also, it's called k-means, as we'll see in a moment, because of these cluster centers. So one way that we can describe a clustering in k-means is via the cluster centers. So here I'm just supposing that k is 3 for the moment. And generally speaking, we want these cluster centers to actually be at the center of the clusters in the end. But we're not always going to be right in the beginning. So we can imagine that we start off with some wrong cluster centers. This just describes some grouping of the data. And there's a difference between groupings of the data and correct groupings of the data. So these cluster centers, they have feature values just like the data points do. And we just write them out to describe the clustering. Now, another way that we could describe the clustering is with data assignments to the clusters. So here again, we have our k clusters, 3 clusters. And let's just say that we happen to assign all the data to the left of this one line as being in one cluster, in the middle as another cluster, and all the data to the right of the other line as yet a third cluster. Then each cluster can be described as a set of points in that cluster, perhaps just a list. And we can describe all of the clusters as the collection of these lists. Now, what's really interesting is that these 2 definitions can interact. So suppose that I have all of the data assignments to clusters. Then I can calculate what is the mean of all of these data points. It's going to be somewhere around in here. And if I do that for each of the clusters, I'm going to get a set of cluster centers. Conversely, if I have a set of cluster centers, perhaps these ones right here, I can get a data assignment to clusters by saying which points are closer to, for instance, cluster 3 than they are to cluster centers 2 and 1. So that would be all of the red data points here. These ones are closer to cluster 1, cluster center 1, et cetera. And we're going to come back to this idea. Okay, so we have to revisit dissimilarity one more time for the following reason. We have this dissimilarity between 2 points, but what about a global sense of dissimilarity? We want to know how clumpy our clusters are in some sense. And so what we're going to do is use the following metric, which I'll explain. The idea is that for each cluster, we sum up over all the data points in the cluster the distance to the cluster mean. So if all the data points in the cluster are very close to the mean, this is going to be small, and that represents clumpiness and sort of a good cluster. And if all the data points are very far from the mean, then that's bad, and we have sort of a disintegrated cluster, and it's not very good. Okay, so our goal then is to minimize this global dissimilarity metric. That will be our objective. And the way we're going to do that is as follows, the k-means algorithm. I'm going to be filling in each of these steps, but at the end, when we're finished, this will become pseudocode that will hopefully be helpful for your exercises. So the first thing we're going to do is initialize the k-cluster centers. This is going to be fundamentally an iterative algorithm. We start with some initialization, and then we just iterate through these steps. Now, this initialization can happen in a variety of ways. There are many, many different ways to do it. I'm going to introduce you to one in particular that you can do. We need to start out these cluster centers somewhere. And what's really nice is we have the data, so why not use the information that, these cluster centers are going to end up somewhere in the middle of the data. So we're just going to randomly sample some points of the data to be the cluster centers. So it's going to end up looking like this, that the cluster centers are actually in the data somewhere. Now, a few key points about this. One, we want to sample without replacement. It's going to be really bad in the end if 2 of the cluster centers are exactly at the same point, because we're basically going to be saying that those 2 clusters are the same, and we're effectively eliminating a cluster, which is not the point. There are other ways to do this. This is very easily done, by the way, in the commands that you've learned today. This is just a sample. For the purposes of this illustration, I'm going to start us off at some other place. But again, it sort of doesn't really matter in just going through this pseudocode. I'm just initializing somehow. But here's a way that you can do it. OK, now we have some initialization. Let's repeat until convergence. What does convergence mean here? Well, what are we doing in this? We're changing. What we're going to be doing is going back and forth between those 2 steps I described earlier. We're going to get cluster centers from our data assignments, and we're going to get data assignments from our cluster centers. So when these stop changing, we're done. So one thing that we can say to say that we're done is the data assignments are done changing. And another thing is to notice that there's no change in this global dissimilarity measure. These are totally equivalent, so you just stop at one of these. OK, so how does this actually work? What are these actual main steps here? Well, they're the ones I described earlier. So we assign each data point to the cluster with the closest center. So we can do that pretty easily. We just, for each data point, calculate the closest cluster, and then make that assignment. So for all of these data points, red is closest. For all of these data points, blue is closest, et cetera. Now, a really key point about this is that none of these assignments depend on the other data points. Every single data point can be independently assigned given that we know the cluster centers. This is very natural to use in this MapReduce framework. Second, once we have this, we're going to assign the cluster centers to be the mean of the data points. So ignore the existing cluster centers. We're just going to look at these red data points, for instance, and calculate their mean. So here's just the particular formula, and here's what it looks like. And now we just iterate. We keep changing until there's nothing else we can do. So we go back here. We say, OK, what are the assignments that we can make? We make some new assignments. Things change, so we keep going. We go back here. We calculate some new means. And this just keeps going on and on until we're done. And we found these nice means for these perfect clusters, which are exactly what we thought would happen in the beginning. And again, this is very appropriate, again, to the Spark framework because of the iterative nature of this algorithm. OK, so this is the k-means algorithm. Great. We've learned it. We're done. That's not true. So with any machine learning algorithm in general, I think it's very important to realize that there's a lot of nuance in it. You can get a lot of different sort of outputs, and you want to be aware, when you get a certain output, what can you do to make it better? What can you do to get a better clustering? So let's first talk about clustering evaluation, and then we'll talk about cluster troubleshooting. So was this any good? Well, let's first think about k-means itself. I think a really important question that you should be asking is it going to finish? Is there actually going to be a point where we've reached this convergence step that I talked about? And in fact, yes, it will always finish. And the reason for that is, remember those two steps I talked about, where we get the cluster means from the cluster, we get the cluster centers from the data assignments and vice versa. Each of those steps, it turns out, you can calculate, always decreases the global dissimilarity, the fundamental clumpiness of our clusters. And so, since we have only a finite number of possible clusterings, this will always finish. Well, is the clustering any good? That's a much trickier question. This global dissimilarity measure, if you think about it, is really only useful for comparing clusterings. I can say, this clustering that I have is better than the previous one, but if I actually look at the number, it doesn't tell me anything. It doesn't say, hey, that was a really good cluster, well done. So what do I do? Well, if you recall from classification, this is a much simpler problem. We have our training data, and we have our test data, and we evaluate on the test data. You just have a number in the end from 0 to 100%, no matter what classification algorithm you run, and it says how accurate you were. In clustering, the picture is much trickier. Nobody agrees on some single measure that just says how good your cluster is. Sure, there are plenty of them out there, but there's no one that everybody agrees on. So what I'd like you to take away from this is probably the best way to tell how good your clustering is to visualize it in some way. Sometimes this is easy. Image segmentation. So here's an image that we want to segment, and here's the output of one algorithm, and here's the output of another algorithm. I think we can all agree that one of these algorithms did a very good job, and one did not. My friend described this as the artsy version. Here we see that there's the tiger, there's the tree. It's sort of everything that if I sat down to label this, I would find the different parts. And here there's just no rhyme or reason going on. So if you have any sort of image problem, what you really want to do is actually look at the images. Same thing with topic analysis. Again, if you look at the first few words in each of these columns, you see that they really go together, that there's some fundamental clustering going on with these words. But here I've created a sort of bad topic with words like president, tiger, lost, parents, opera. And while you can make, I'm sure, a very interesting story out of those words, it's not actually, they don't go together at all, right? So again, this is the sort of thing you can look at after the fact, and you can really see, did my clustering algorithm do well? Some other tools that are useful for this are things like ggobi. So this is an open source tool that lets you visualize in somewhat high dimensions. So humans have issues with 4 dimensions and above, any sort of visualization, and arguably in 3 dimensions a lot of the time. And the nice thing about ggobi is that it projects into 2 dimensions, your multiple dimensions, and also any particular clustering that you might have of your data points. Now, there are some limitations. This can't deal with a huge number of dimensions, as sometimes occurs. For instance, Ariel talked about words. Maybe you have one feature for every possible word, but the English language alone has 50,000 words by some estimates, so that's 50,000 features. You're not really going to visualize it with this tool. Also, if you have a lot of data, there's no getting around the fact that if you plot it, you're just going to get a big blob. So here you'd have to do something like subsample your data, but it is still a very useful tool in some cases. Now, I did mention that there were metrics for comparing clusterings, and I just want to go over a few of them so you're familiar. And they're not totally useless. I don't want to give that impression. So one option is to sum over all of the intra-cluster dissimilarities. So what are we doing here? We're summing over all of the dissimilarities between 2 points that are in the same cluster, and we're not summing over all of the points that are in different clusters. Another version of this idea is related to cross-validation and the sort of training set, test set dichotomy that Ariel was talking about. And what's happening here is that you learn your clustering on some separated training set. So you decided what it was in the beginning. You put out 25% of your data for testing. And then you just calculate your clustering measure of goodness on the test set. And there are a lot of other indices that you can use. So for instance, the RAND index compares two clusterings, and you don't have to have a measure of dissimilarity. So this is nice if you're actually using two very different methods of clustering. So here, all you're doing in the RAND index is looking at, hey, every 2 points I have in my clustering over here, suppose they were clustered here, are they clustered or are they not clustered over here? And making that kind of comparison. Likelihood is very common when you have a model-based method. And there are also a lot of domain-specific measures. So if you're working with text, if you're working with images, there tend to be specific measures that people respect in those domains. Yes? Excuse me? Oh, yes, that's a great question, and one that I will be answering shortly. The question was, how do you choose the value of k? So how do you choose the number of clusters? Getting there in a moment. Thanks. Okay, so yeah, clustering troubleshooting. How do I choose the value of k is a very specific question here. But let's go back first to k-means in particular and talk about issues that we might have just with k-means. So I'm just going to go through this really quickly. In k-means, it might not be fast enough. Maybe it's still too slow. This is always a problem, right? I'm just going to mention that there are various methods, sort of for handling your data to speed up k-means. And there's also an online version if you need something that isn't batch. But I'm not going to go into that right now. Something about the algorithm I described earlier is that, yes, at every step, the global dissimilarity decreases. That does not mean that I find the global lowest dissimilarity for every possible clustering. It means that I keep going lower and lower until I stop and I find a local optimum. But there might be some other global optimum over here, so what do? One very simple option is multiple initializations. Also, this sort of gets into there are many different ways to initialize your cluster centers. Some are better than others, and so you might want to consider something like that in a practical application. Also, this may not even be the problem you're asking about. And this really gets into the question that the audience member made. We want to look at what do we really mean by grouping similarity and data. So grouping in particular. What we've been describing so far is called hard clustering. Each data point belongs to one and only one cluster. That's hard clustering. And then a particular subset of that problem is where we assume that the number of clusters is fixed. So as an example of where you might actually want to use that is image compression. So we have an initial image over there on the right-hand side, and it exists in some color space, say 256 colors. And the way that I'm going to compress my image is I'm going to say, hey, I'm just going to use some very much smaller color space, say 3 colors, and I'm going to assign each of the data points to some color, one of those 3 colors. And so I have to choose what are the best 3 colors and what are the assignments of the data point to the colors. Well, this is exactly a problem for k-means. The 3 colors are the cluster centers, and the data assignments are exactly the data assignments from k-means. So this is where you'd want to do a k-fixed problem. But sometimes the number of clusters is unknown. What do you do then? So for instance, consider I have this data set. The sort of naive thing that you might think is, well, we already tried a bunch of different clusterings, and we calculated our global dissimilarity for each of those clusters, and then we said which one was the best. Why don't I just do that for a bunch of different values of k? Here's why not. Here's the best clustering you can come up with. Every data point belongs to its own cluster. It's exactly 0 distance from the cluster center, so the global dissimilarity is 0. The global dissimilarity is always positive, so it's perfect. You just can't get any better than what I've just described. And in fact, in general, if you calculate the global dissimilarity for different values of k, it's just going to be decreasing like this. And that's not an optimization problem that you can solve or solve in a meaningful way. So there are some heuristic methods to deal with this. One of them is that traditionally people find something called an elbow in the graph. You can sort of see that there's a really big difference in the behavior before this point and after. A way to be more quantitative and specific about that kind of idea is something called the gap statistic. there are various ways to turn this into an actual optimization problem. So what we can do is we can calculate this global dissimilarity that we saw earlier, and then add a penalty for each new cluster. So we end up getting a graph like this, which is something we can actually optimize and find a minimum for. Also, there are various model-based methods. You put some sort of Bayesian prior, a distribution over the number of clusters, if you're familiar with these types of methods. And in that way, you again have the potential for any number of clusters. Okay, so we have k fixed, k unknown. What if you're not so interested in k as much as you really need your clusters to be consistent across different numbers of clusters? So for instance, imagine this graph. These two data points, when I go from 3 clusters in green, I want them to still be clustered when I go to 2 clusters in blue. If this consistency is really important to you, do not use k-means. K-means has no guarantees that if you use different numbers of clusters, if you even use a different initialization of your clusters, that you will have data points that are consistently in the same cluster together. They could end up totally separated. That is not going to happen with k-means. In this case, you would have to use something like hierarchical clustering, an example of which is agglomerative clustering. There's also something called soft clustering. So hard clustering, each data point belongs to one and only one cluster. In soft clustering, you realize that, well, sometimes that's not exactly what I'm looking for. Maybe my clusters are all sort of smushed together, and in particular, I have data points that are really deeply inside of a cluster, and I'm really sure that those data points belong in that cluster. But then maybe I have some data points that are on the boundary, and I want to express that in some way, that maybe that data point belongs to the green cluster, maybe it belongs to the blue cluster. And in this case, I want to use something like fuzzy c-means, which is an extension of k-means, or a mixture model, like a Gaussian mixture model. What about similarity? K-means is sensitive to outliers. This is fundamentally to do with the Euclidean distance that's used in it. So for instance, consider this data. These are the distances that a number of people made when they long jumped. And I could say, oh, hey, I see this data, and it looks like maybe there's a pattern here of sort of 2 different clusters. So I predict k equals 2, and I try to find these clusters. Well, when I run k-means on this data, I find, oh, this is a cluster and this is a cluster. Well, that's not what I was looking for. This person just didn't really make it off the mark. What I really wanted to find was these 2 guys. So there are a variety of things that you can do here. One is you could just get rid of your outliers. But if you actually want to keep all of your data, then another option is changing the distance metric. So not using the Euclidean distance, using something else. One option that comes up is k-medoids, where instead of taking a mean of your data in the one step, you take a median. K-means yield spherical clusters. When is this bad? Here's a particularly egregious example. This looks like a cluster to me, and this looks like a cluster to me, but it won't look like clusters to k-means. These points are very close in Euclidean distance, and these points, despite being in the same sort of real cluster, are very far. And so k-means would split it like, 1 here and 1 here. So what do I do here? If I know that my data looks like this somehow, then I want to make some sort of transformation into maybe polar coordinates, use a different definition of similarity, or it turns out agglomerative clustering would also be able to deal with this type of data. And that leads me into other issues of k-means to do with the data. It requires continuous numerical features. So if I'm working with text, for instance, or images, then I might need to specify some similarity that's very specific to them. Or I could transform my data to be in the format that k-means needs. And this really gets into some of the points that Ariel was making about featurization. What do I need to do to my data before I run k-means on it? So first of all, I need to ask, is my data set featurized? So this is what my data might look like. Somewhere it's floating around on my computer. I have this person who was poorly named by their parents, and they have an age, they have a height, they have other information about them, perhaps some text associated with them. And I want to put this all into a feature vector that we've already talked about. And so this is what this looks like. I've featurized my data. For each feature, for each element that I'm interested in, I have some particular value in my data, and now my data is comparable across all the different people in my database. Now for k-means, it's not enough to just have these different features. I also have to have them be continuous numerical values. So here I need to think about, are they continuous numbers? Well, 5'7", that's not quite a number yet. I really need to turn that into maybe inches. And this education level, it was bachelor's. Well, maybe I need to come up with some sort of numerical scheme for that, assigning 1 to a high school degree and 2 to some of college and 3 to a bachelor's degree, et cetera. So anyway, basically the idea here is I come up with a numerical scheme. Okay, at this point, I can take this data and I can input it to the k-means algorithm and I will get something out. But I should really be more careful for the following reason. Are these numbers commensurate? Here's an issue that you really want to think about before running k-means, and that's the following. So a lot of times when we see graphs in papers or something we're reading, we'll see something like this. This axis is 0 to 1, this axis is 0 to 10, and this graph is very nice, it's pretty. This is not what k-means sees. In k-means, we sum up over all of the differences squared. So if this axis is on a fundamentally different scale than this axis, it looks like this. We no longer have 2 well-defined clusters here, we just have this one big line blob of data. And so if we want to run k-means on this, we have to perform something called normalization or standardization if we want to separate those clusters. And so an example of that, if we want to not have to deal with outliers, is to subtract the mean and divide by the standard deviation of the data on each of the different coordinates. Yes?
That makes it very hard to use with categoricals, doesn't it?
Oh yeah, absolutely. I mean, I think the categorical issue comes back way back here where we turned this data into continuous values. So if you want to use k-means with categorical data, you have a few different options. One is you can think about, okay, I have these different categories. Maybe my people, I have census data, people live in urban or rural category or urban or rural areas. You can think about defining a similarity specifically for those different categories. So how similar are each of my different categories to each of my other different categories, fundamentally coming up with a matrix. Or if you possibly can, turning those categories into integers and pretending that they're continuous values. So yeah, it's definitely a tough problem. And it has a lot to do with what those categories actually are, as I think you can imagine from that. Yes?
Or you can make a Boolean vector out of it. If you have like 5 categories, you can just make a 5-sided.
Right, yeah, so you can absolutely make a Boolean vector out of it. You want to think about what's going to happen here, whether this is the appropriate way to represent that, because you're basically going to get a distance of 0 then whenever the 2 categories are the same, and a distance of 1 when they aren't. So if that's fine for you, then absolutely, Boolean vector is the way to go. Okay, so we've standardized, we've normalized, et cetera. Another issue is, are there too many features? Maybe we have this 50,000 word feature set from this bag of words model that Ariel was describing earlier. A lot of times we really just need to pare those down. So one option, a really nice option, is called principal component analysis. And I'm not going to get into this too much except to say that the basic idea is we think that our data really only exists in a very small number of dimensions, but it's being expressed in a high number of dimensions. So a nice cartoon for this is, maybe I have 3 cameras, and they're looking at this ball on a spring that just moves in a line, just a straight line. It's a very boring ball. And so for each of these cameras, I have 2 dimensions of information, the horizontal axis and a vertical axis. But fundamentally, we know that there's only really 1 dimension of information here. So PCA is going to take all of these dimensions and fundamentally rotate the space that they live in until we have all of the information in the first few dimensions. And then what we would do is we would take those first few dimensions, cut off the rest, and we'd have a much lower dimensional data feature space. A much simpler option is to just do feature selection and get rid of a bunch of your features. A lot of times you can use domain information here. So for instance, as Ariel pointed out, if you're working with text, we know that stop words, so-called stop words like if, the, and, of, you can get rid of those. There's not too much information. Yes?
So if k-means itself, how does it perform if
Mhm.
or you just don't do feature selection at all. Let's say that you have the computational budget to
Right.
actually do this.
Yeah, so I think it definitely, well, first of all, let's deal with the redundant features. If you have a redundant feature, if you have, for instance, exactly the same feature, then you have to really look at this, this distance metric again and think, well, what's basically going to happen is it's going to be counted twice. And so you're sort of, it's almost like you're scaling. You're just doing a disproportionate effect, or giving that feature a disproportionate effect.
So let's say you go ahead and standardize it, right? And then after that.
Right, but that won't be covered by standardization, right? So you will have standardized one particular feature alone, but you'll still be counting it twice here. So it's like scaling that you can't get rid of in some sense. Now, if you have a ton of different features and they're all noise and they're not doing anything, then what's going to happen is here you're going to get some distance for them just because of the noise, and that's going to end up swamping out your signal. So this really does have the issue that I think we fundamentally got into at the very, very beginning of this entire camp of you want data to be a resource, not a load. And here, unfortunately, it can be a bit of a load. So if you have just a ton of features that aren't doing you any good, you really want to prune them if at all possible beforehand. And actually, this idea of feature selection, I could really, somebody could really give an entire talk on that, an entire 1-hour talk just telling you the many, many ways to do it. And I just want to alert you that PCA is very common, especially for images, to get a bunch of principal components for your images beforehand and then give that to k-means. And also just getting rid of many, many features. So another domain-specific example would be, let's say I have words. I'm doing some sort of text classification, or sorry, text clustering. Then what I might do is get rid of all of the words that only occur once because they're not giving me any information. Things like that. Yes?
When it comes to the number of iterations in the k-means algorithm, is
Yeah.
there some rule of thumb for the number of iterations it takes?
Yeah, no, that's a great question. Unfortunately, I don't know of any particularly good way to know in advance. What some people do is if it's taking far too long and you've tried other speed up mechanisms, is to just say when it's changing a very little instead of when it's actually stopped changing to stop. But I think a little bit of it is a bit of a black art. Yes.
So with respect to like K, the way you said, you would plotted this graph with increasing K.
Yeah.
If you plotted a second graph keeping like the data aside, as you said,
Mm-hmm.
and saw where both the Ks were going low, won't you get a pretty good estimate of what K should be? Like why would that?
Right. Yeah, so that's absolutely something you could do. You could do some sort of cross-validation idea where you leave out some test data set and then see how far things are from that. I guess at that point, you might almost be saying, I think you still have somewhat of the same problem because you can get to the point where you just say, well, if everything is in its own cluster, then whatever closest data points there are to my test set, that's sort of the best I can do. So let me see if there's a way I can make this clearer. So let's say I have one test data point out here, and here's the rest of my data. Then the closest it's ever going to be is whatever closest data point in my training data there is. Because any other mean is going to be over here. And so fundamentally, I still have the issue that if this were in its own cluster, that's going to be the closest cluster. So just something to think about. Yes?
How do you deal with too many data points? Like the number of data points is 800 million, number of Facebook users. How do you deal with that?
So in that case, you really want to take advantage of the fact that the first step in the k-means iteration is entirely parallel. And the fact that you can calculate which cluster center each data point belongs to completely independently of the other data points. And in particular, in most usual cases, you're going to have a low number of clusters and a high number of data points, and so that won't be so computationally expensive. However, there are still even better ways to do it than to just keep track of that. And that comes back to this bullet point that I had, that there are sort of these data structures that you can keep your data points in that will help you make that computation even faster. And they take the form of like KD trees, use of the triangle inequality, things like that. And so I had some references in my slide earlier. It might be something that's useful for you to read up on if you find that k-means isn't enough for you, just taking advantage of the parallelism on its own. Yes?
Two questions are related to each other. One, is k-means clustering suitable in cases where
Right. So for the first question was, is k-means clustering suitable when the entire data set cannot be loaded into memory? There is an online version of k-means clustering. So in that sense, yes. And basically, it takes advantage of the fact that this is fundamentally an optimization problem. And there are some basic ways that you can turn optimization problems of this type into online problems. The second question was, remind me? Outliers, yeah, how do you get rid of outliers? So I don't have a really good answer to that, and I don't know that there is a really good answer to that. I know that in practice what a lot of people do is remove them by site, which I don't recommend, because that seems really not based on any statistical knowledge. Things that you can do, I mean, it sort of depends on your data, right? So if things totally don't belong in your data, then maybe that's something appropriate to do. I mean, certainly in this long jump example, well, I don't want to go all the way back, but in the long jump example, it's pretty easy to tell what's going on with the outliers. These weren't people that you really wanted to even include in your data set. You were really interested in people who passed the mark. I think that one ends up being very domain specific.
Could you apply key box type of analysis to identify the outliers and see them to
Yeah, in certain types of data sets, you can always say, like, here's some 95% interval for the data, and I'll get rid of anything beyond it. I mean, there's some sense in which all of those ideas are somewhat ad hoc. One option for you, if you don't have a data set that's far too large to handle it, is to use a model-based method where your model includes the fact that you are expecting outliers. And in that case, I mean, model-based methods are really powerful in a lot of ways that you can really tailor it to what you expect your data set to exhibit, the sort of behaviors. So, k-means says, I expect these perfectly spherical clusters. I don't even expect ellipsoids. I expect, all of my clusters to be sort of equally represented. If you don't expect those things and you're able to do it, a model-based method can incorporate your prior ideas about what you expect in your data. Yes?
How do you handle normalization when you have outliers? I want to get outliers.
Yeah. So I would say that that's sort of why it's important when you're doing normalization to probably not just say, oh, I'm going to put everything between -2 and 2 and take the max and the min and put it in there. One way to deal with it is, as I said, subtract the mean and divide by the standard deviation. That's still a little sensitive to outliers. So you might do something like a quantile interval instead to try to be less sensitive. So you might say, hey, I'm going to put the median at 0, and then maybe the 10th or the 25th quantile here, and the 90th or the 75th quantile here, depending on how many outliers I expect. Great. Okay, so we want to get rid of features. There are many ways to do it, and there are domain-specific reasons to change things. How am I doing on time? Is anybody? Yeah, I forget where the new time change went to. Oh, okay, great, sweet. That's all I wanted to know. Thank you. Okay, so let's go through an example. I've sort of said all these issues with, oh, k-means. Here are some issues that you might have with it. There are all these ways that it fails, but fundamentally, the take-home message I want to give you is that k-means is extremely powerful. I just want you to be aware that it's not perfect, that it has a variety of issues you should be aware of. If you can tailor your data to those issues, that's great. It's just not a black box. That being said, it's used in just a wide variety of areas. If you're going to do any clustering algorithm, you're probably going to do k-means, at very least first, before you do another clustering algorithm, and you might well use it to initialize your next clustering algorithm. So it's just extremely popular, and I'd like to go through just a sort of little example that I think is kind of neat of using k-means in practice in a way that returns some really interesting results. So here what we have is a string of DNA, A's, C's, T's, and G's. And so we might think, hey, what if, we're all coding a lot here. What if DNA is made up sort of instruction words, like some sort of code? I'd like to, put that hypothesis forward. Maybe this GAA means something, and this TGG means something. And that's how DNA is really structured. How could we sort of test if that's true? Is that something that we can play around with? So I'm not going to take a really formal testing approach to this. I'm just going to play around with the data and say, is this true? Which of these lengths is correct, if it is true? So this comes from a nice tutorial on the internet that you might want to look up. So our data is going to be about 300,000 DNA, 300,000 kilobyte long DNA substring from some bacteria. We're going to break it down into a number of data points, because right now all we have is one giant string. So we're going to break it down into substrings of length 300, non-overlapping, so just this one, et cetera. And this is nice because this would contain enough words to be, a reasonable amount of words, even if our words are length 4. And then for each substring, we're going to get a count of all the possible words of a given length. So let's just pretend we're looking at words of length 2 right now. What does this look like? Well, all the possible words of length 2, I could list them out, AC, AA, AC, et cetera. So for our first substring of length 300, we can count the number of times each word occurs. So AA happens to occur 6 times, AC occurs 10, et cetera. And this gives us some sense of the distribution of words. And so we might think that, imagine that this string really was some sort of code. Well, in code, I write the word if a lot and the word end a lot, depending on what I'm coding in. And so there are some words that occur a lot more than others. And maybe main occurs, very few times because it just starts off all my code. And so we would expect there to be some sort of special distribution if this really were a code. Well, let's look at PCA. Remember, we can reduce the dimensionality of our data set with PCA. And let's look at the first 2 dimensions in PCA. Well, there's not much going on if we pretend the words are length 1, and same over here. And then, whoa, 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 look at all this structure over here. There's definitely something going on here. And so we might think, hey, this is a lot of structure. Let's investigate this further. And in particular, I think that the kind of structure that we're seeing here is very naturally seen as clustering structure. You could see that there are sort of maybe 6 clusters here, maybe 7 if you include this weird middle part. And so we can investigate this by using k-means to identify these clusters. So first of all, we need to look at substrings of length 3, or sorry, words of length 3. So we're going to get the counts for each word of length 3. And again, this sort of summarizes some sort of distribution of the words, which we expect to be very specific to if there's some sort of code. And then we can normalize it, as I suggested earlier, subtract the mean and divide by the standard deviation. And then we get these new numbers, which, now that we've featurized our data by putting it in this table, and we've normalized it, we're ready to put it into k-means. So we do that. We take our normalized data. Let's pretend k is 6, because that seems sort of reasonable from looking at PCA. And now here's just one key point. I said earlier in this talk that a lot of times what people do is they'll take their data set, they'll use PCA to reduce the dimension, and then they'll put those coordinates into k-means. That's not what I'm doing here. In this particular case, I'm visualizing the data set with PCA, but I'm actually putting that full distribution of words in as my data set. So if I see something, if I see some sort of structure when I plot this using PCA, it's almost like those 2 points are corroborating each other. And in fact, that's what's the case. So I visualize the clustering with PCA, and it looks really good. These are exactly sort of what we expected the clusters to be. And I can do this with k equals 7, and this is sort of even more interesting because we do separate out this middle part. And so at this point, because we did this with k-means, we have a color for each of these data points. And remember, the data points themselves are these 300 length substrings. So we can actually color the entire DNA string that we have with all the different colors from the different k-means clusters that we had. And so at this point, we've been doing this exploratory data analysis is really what's been going on here. We got some new data, we got some DNA, and we thought, hey, maybe there's a pattern in it. I'm going to investigate with the tools that I have. And now we have to sit back and think about what we know about our problem to sort of understand what's going on here. Well, it turns out if you think about it, so where we started, our 300 length substring could have been, supposing that DNA is actually composed of words of length 3, it could have been at the beginning of a word, it could have been at the second letter of the word, or it could have been at the third letter of the word. Genes also sometimes go the other way. It could have been at the first letter here, it could have been the second letter here, or the third letter. It's exactly 6 clusters. Now what's this middle part? It turns out in DNA, there are genes, so genes can go forward, and genes can go backwards, and they encode information, and they have this coding structure. But there's also non-coding regions, regions where nothing's really happening, and we wouldn't sort of expect those regions to have a very strong direction in any sense. And that's what's going on here. This is the non-coding part of DNA. And so I think this is a really neat example that, we came in knowing basically nothing about DNA, and we figured out that there are these fundamental units of words. And it turns out, by the way, that these words are called codons, and they encode different amino acids when your gene is telling you how to make a protein. So I just want to leave you with a few points. We've covered one big idea, clustering. In fact, we've covered a few big ideas. We covered all of machine learning. So good, go us. But really, more concretely, we covered this particular implementation, k-means. So you really know at this point, in some sense, how to go out and perform clustering. Or at the very least, you can look at this slide later and code it up to the best of your ability. But I think we really got a sense that machine learning isn't a black box, that you don't just put something into k-means and get amazing, perfect answers out. I think a lot of the questions that people asked today really reflected that we have a lot of different types of data, and you have to think hard about what's the correct way to send that data into k-means, and what's the correct way to interpret that data when you get it out. And this really fundamentally comes back to Ariel's slide that machine learning is a pipeline, and even more than that, it's sort of a workflow. Thank you. Oh, is there a question?
So you said machine learning is not a black box.
Mm-hmm.
So is that possible to make it black box?
Yeah, and I think that's a great point, that that's really what the field of machine learning as a research area is probably aiming for, to have it be more of a black box. And that's a goal, but I don't think we've achieved it yet. And so given the constraints that we have, you just want to be aware of those constraints. Oh, yes.
I guess this would be a question for both you and Ariel, but I think it was good for us today to kind of learn the underpinnings of these algorithms, kind of what's inside the box. But is there anything that I should interpret from the lack of mention of projects like Apache Mahout or like Revolution Analytics port of R to Hadoop? There's so much to tweak inside of these algorithms, but there are implementations out there that were sort of oriented towards getting us away from MATLAB and doing stuff more on big data platforms.
Right.
Do you guys look at those projects at all inside of AmpLab, or are you kind of not interested in what's going on in those projects, or do you guys have any kind of comments?
So do you mean me personally or the AmpLab as a whole?
Well, I don't want to force you to speak.
I can speak for me personally. My research. Oh, sorry. The question is.
Think of Mahout or
Okay.
the other kind of projects out there, just more black box clustering
Right.
and classification.
So what do we think of Mahout and other projects out there that perhaps more black box all of these issues, classification, clustering, et cetera? Actually, so I have a sort of a different answer to that question, and that is I don't think that I don't think that regardless of the answer to whether we've brought those into the AmpLab framework, that reduces in any way from what we've been accomplishing today. It's sort of a completely different question. I think that again, coming back to what I was saying earlier, that there's some sense in which, at least at this point in the development of machine learning, you can't black box everything. And so even, let's say we do include a ton of different useful implementations into the AmpLab stack of all of these algorithms. I think it's still really important for everybody in the audience to understand what's really going on under the hood, because some of these things are just so domain specific. Should I normalize my data? Sometimes it turns out you really do want those differences, things like that. And so you want to know what your algorithm is actually doing so you can tell it, oh yeah, this is the change I need to make.
Wait, so I'd like to follow up on that, actually. Yeah, we're coming at you from all sides here. Yeah, so with respect to those libraries, so there are a wide variety of different machine learning libraries out there, many of them are not for big data, right? So many people in this room probably have heard of or worked with R, which incidentally, is a great tool, particularly for getting your feet wet with many of these algorithms. Pretty much, many algorithms you might think of are implemented in R, but of course, this is not on big data. This is great if you're like on your laptop and you just want to start exploring. As you said, there are, people have built on top of R this thing called Revolution Analytics, which kind of makes a sort of, it's basically a company that supports the open source version of R, right? So they commercialize R. But even, even there, and there are a variety of other solutions, people have mentioned Apache Mahout. Many of these, I think, are still pretty nascent, particularly with respect to automation. As you say, there's still things to be tweaked. Apache Mahout, is indeed, working on a variety of different algorithms on top of Hadoop. But again, this is, I think, there's a lot more work to be done on the side of automation. So I don't think there really is like one black box solution that you can like just plug into and just, suddenly that's going to just train your classifier, and tweaking is not going to do anything for you. If that does exist, someone in the online audience or here knows about that, tell me, because I'd love to know. But as far as I know, this is work in progress, and potentially we could see something like that coming out of the AMP lab at some point. I think Spark is a great platform for building on top. For doing that, like, this isn't just idle talk. I've implemented, a decent amount of stuff on top of Spark, and it really actually is well suited to many of these tasks. But
All right, thanks again, Tamara.